Hello to anyone who is watching this demo video of our OpenBot project. Welcome. I'm Sardeep Banerjee, and this is the demo video for Team Mach 25. And in this demo, I'm basically going to go over our architecture, what our product basically does, and how it fulfills those issues that we are going to discuss about. So basically, our project is based on cybersecurity. It falls under the cybersecurity track. And here we are trying to solve a very particular problem where autonomous agents, agents like maybe agentic AI, for example, something that came out very recently is called OpenClaw. It was previously called CloudBot, and then it was I think like named to MoldBot or something, and now it's currently called Cloud OpenClaw. So basically, OpenClaw is an agentic AI application that can basically handle any task as your own personal assistant. And there are many structural flaws in this case, especially like security flaws, because to be precise, there was a recent case where researcher gave access to OpenClaw, like her emails. So OpenClaw mistakenly deleted very important emails, right? Like it deleted a bunch of emails that were really important to her, and at the end, the AI just mentioned that it was really sorry for this catastrophic damage, but the damage was already done, right? So how do we mitigate this change? Is there a way to prevent such damages, and what to do? How do we roll back the situation if the damage is already done? So this brings us to our architecture. Basically, our architecture is called OpenBot, which is basically it's like an extension over OpenClaw's source code. So OpenClaw's source code is public on GitHub, and we are adding an extension over it. But technically, to be precise, our architecture behaves kind of like a kernel user application. So, like in operating systems terms, our product is basically like a kernel application that has more privileges than the actual instance of OpenClaw itself, right? So our product OpenBot has more privileges and has the access over OpenClaw. So that's the main idea here. And what we are trying to do here is we are solving very specific problems. The first case is where so basically the first thing is we need something to detect how we are gonna basically analyze threats, right? What makes a prompt or like an action malicious in this case? So for that we used so this function basically contains a semantic analysis algorithm that basically determines if it basically like classifies if a function is malicious or not. If it's malicious, it will give it a priority score from I think 1 to 10, and based on that we pass it to a scheduling algorithm. Basically, there are many scheduling algorithms like round robin and shortest first scheduler. But in this case, you might have like been known, like you might have like known them from your operating systems classes, maybe, but people like who are like not CS related. So basically, scheduling algorithms are used in everyday operating systems. It's used to make sure every application is responsive and can run concurrently and like on any devices. So we make sure that those processes are like the threads that we analyze, they are received at a scheduling algorithm. We have implemented a very simple version of, not a simple version, but a very concise version of multi-level feedback queue, and it has two parts. Multi-level feedback queue has two parts. So it has the actual multi-level feedback queue, and the second part is we have implemented a dispatch table, which basically acts as how an interrupt table works in operating systems terms. So basically, it just helps us to index what to do if a particular type of threat is analyzed by, let's say, the scheduler in this case. So that's the second part of this algorithm. After this is done, we basically then handle that error by sending the data from the scheduler to the dispatch table and handle it. Now, for handling, there are two cases. The first case is basically where the threat is cached. The threat is caught before any damage was done. In that case, we don't need to do any changes or anything extra, because we can like just kill the process that was like causing like was about to cause something malicious and like some sort of a like catastrophic damage, right? The second case is a pretty serious case. So in this case, the damage is already done. So the machine learning model that predicts whether the process or like the command or the action is malicious or not actually failed in its first pass to predict if it's malicious or not. So in this case, what it does is it will basically, so what we have done is we have changed the definition of delete function in C++. We have changed the definition of delete function in C++, and this one is basically related to Linux kernel only. So whenever the delete function will be called, it will actually forward to the move function, which basically means that we have a temporary variable or temporary folder where those deleted files will be moved to, and it will also have some kind of metadata which will store the information needed if we need to roll back that information back, right? So in this case, if for some reason we found that some damage has been done, the data is already stored in this temporary folder, so we just go back and pick it up from there. And that kind of helps us prevent any catastrophic damages in this case. And this leads us to the third part, which is basically dashboarding. So we have implemented a very like concise way to show every single intercepts we have like processed in our OpenClaw instance. So here we kind of keep track of all the logs or all the threads that were like issued, and how many were intercepted or like handled by our system handler, and we keep track of them. And this is like a dashboard which basically gives us the idea of using it, right? Another thing would be to basically use moldbot, right? So if I not moldbot, I think it's called OpenClaw, like in this case. So if I bring this tab here, and for some reason, let's say I just like I run our program here, right? I run our program, so docker compose down and docker compose up. So in this case, what happens is we are running our docker container. So if we give it a moment, we should see the dashboard being changed here. So this is the actual demo. So I explained the main stuff here. So you can see that it's currently, I think, 5:53 a.m. So it's updating if it deems like something's malicious in this cases. So at the start, there are some commands that might be deemed malicious by our system handler. So that's the reason we have a few of these errors popped up here. Aside from that, let's get back to one of the few examples that we have. So I'm gonna basically discuss about this example. So this is an example for case one where the damage was not done, was not done yet. So in this case, we ask OpenClaw to create a temporary file named secretpasswords.txt using the command line, and then permanently delete it using the rm command. Now, like at the very start, we know that passwords.txt sounds pretty serious, right? So it might contain secret passwords. So permanently deleting it might be harmful for the user, even if like the user have intended this in this case. Now, what do I mean by that? In this case, the natural language can be interpreted in many ways, right? So even if the user said a thing in a sarcastic way, the AI might not actually be able to interpret that in that way and can cause catastrophic damages. So in this case, our algorithm will basically stop the AI from executing, or it will kill the process ID of this OpenClaw instance, and therefore preventing any catastrophic damage or any deletion being done. So if I run this, basically you can see that it actually didn't give any output because a security firewall was hit. The OS interceptor was loaded, and we also have a quarantine directory ready in case like if some files were deleted in this case. So the quarantine directory is the temporary like directory that I mentioned in the examples. So here what happens is and at the end the actual OpenClaw instance will like pop up, and in this case it actually won't delete the file. It actually won't delete the file, and we can also check that from here. It's not technically here, it's in the Docker instance. So I'm gonna keep this pretty short. I think the video is gonna like has like gone pretty forward. So if we see the logs here, we can see that the assigned like priority is 3, right? The assigned priority is 3, and there are many logs that are sent here. So these logs, if they are deemed worthy or like they have a higher threat, they will be they will be sent to the Firebase dashboard to basically log and keep a track of what kind of errors were caused by this, like, right? So what kind of errors were caused by this? So that's basically it. Um, it's a pretty short demo in this case. So I guess thank you for watching.